As promised, we are now going to prove the law of quadratic reciprocity. Well, if we're going to prove it, we'd better state it. Suppose P and Q are both odd prime numbers and they're not equal to each other. Then the product of the two Legendre symbols, P over Q and Q over P, is -1 to this power, phi of P over 2 times phi of Q over 2. Here's where the term reciprocity comes in. This looks like the reciprocal of that. But they're not actually fractions, remember. These are Legendre symbols. We're not just multiplying two fractions together. We are computing two Legendre symbols, and the law of quadratic reciprocity says the product of these two values is equal to -1 to that large exponent there. So this video will be dedicated to proving this statement. This will be followed by various examples that show just how much this helps in computing the value of Legendre symbols. For now, however, let's assume that this statement has been proven. We're going to manipulate it a little bit to get some very convenient statements. Both of the two Legendre symbols are either +1 or -1. They can't be 0 because P and Q are definitely relatively prime to one another. They are both odd prime numbers and they're not the same prime number. If the product is equal to 1, that tells me the Legendre symbols are the same. Okay? Both of them are either +1 or they are both -1. Either way, their product is 1. Similarly, if the product of the two numbers is 1, they had to have been the same. We don't actually know whether they are both 1 or whether they are -1. What we conclude is, if the product of the two Legendre symbols is 1, then the two Legendre symbols are equal to each other. Either they're both 1 or they're both -1. We don't quite know yet which one. If, however, the product of the two Legendre symbols is a -1, then one of them had to be +1 and the other was -1. I don't necessarily know which is which, but I know the two values are opposites of one another. Writing it like this, I am not claiming this is 1 and this is -1. I'm simply claiming whatever this one is the opposite. Either a 1 and a -1, or a -1 and a -1. So if the product of the two Legendre symbols is 1, they are equal to each other. If the product of the two Legendre symbols is -1, they are opposites. So suppose P and Q are two distinct odd primes. Here's the statement of the law of quadratic reciprocity. When the exponent is even, phi of P over 2 times phi of Q over 2, if that's an even exponent, on the right-hand side, I get -1 to an even power, meaning I get a +1. So if the exponent is even, the product of the two Legendre symbols is +1, and therefore they are the same as each other. When the exponent, on the other hand, is odd, the right-hand side is -1 to an odd power, that's -1. And as discussed on the previous slide, if the product of the two Legendre symbols is -1, then they are opposites of one another. Now the exponent is the product of these two numbers, phi of P over 2, phi of Q over 2. The product of two numbers is even if and only if one of the original numbers is even. The product of two numbers is odd if and only if they're both odd. Now phi of P over 2, we've seen before, is even or odd according to whether P is equivalent to 1 mod 4 or 3 mod 4. So here's the statement of the law of quadratic reciprocity again. Altogether, if either P or Q is equivalent to 1 mod 4, then one of these two numbers is even, and if one of them is even, the whole exponent is even. Then I get -1 to an even power, so this becomes +1. If the product of these two is +1, then they are equal to each other. So if either of the primes I started with is equivalent to 1 modulo 4, the two Legendre symbols are equal. On the other hand, if they are both equivalent to 3 mod 4, then both of these numbers are odd, then their product is odd, -1 to an odd power is -1, the product of two Legendre symbols is -1, means they are opposites of one another. So this is how we're going to apply the law of quadratic reciprocity. If both primes are equivalent to 3 modulo 4, the two Legendre symbols are opposites. If either one or both of them is equivalent to 1 mod 4, the two Legendre symbols are equal. So finally, we're just going to formally restate it in those terms. Suppose P and Q are two distinct odd primes. The two Legendre symbols are equal if either one of the primes is equivalent to 1 mod 4. The two Legendre symbols are opposite if they are both equivalent to 3 mod 4. But now let's go ahead and prove the original formulation. Once we prove the original formulation, this version up here, this is the equivalent version that we will be using in problems. Finally, on to the proof. Again, here's the statement of the law of quadratic reciprocity. Now, P and Q are both distinct odd primes, so they're definitely both relatively prime to each other, and they are both odd, which means we can apply Eisenstein's lemma twice. First, in computing this Legendre symbol, Q is an odd prime, P is an odd integer relatively prime to it. On the other hand, P is an odd prime and Q is an odd integer relatively prime to it. So if I apply Eisenstein's lemma twice, one of them is going to look the same as it did in the previous video. In the other, all of the P's and Q's get switched. So f of P is computed like this, but g of Q is computed like this. All of the P's and Q's get switched. So then, by Eisenstein's lemma, the Legendre symbol P over Q is -1 to the f of P, and Q over P is equal to -1 to the g of Q. Okay, this is why we proved Eisenstein's lemma as a whole separate video, so as to save 15 minutes at this step. So now let's take the product of the two Legendre symbols. The product of the two Legendre symbols is now just -1 to the f of P plus g of Q. It's not required, but it would be enough. If we can show f of P plus g of Q is exactly equal to this product, well then, the product of these Legendre symbols is -1 to this power, which would be the same as this one. So what we're going to do is we're going to draw a grid. Okay, might be a little bit of a surprise, but yes, we're going to draw something. This is our goal. We want to show f of P plus g of Q is this product, where f of P and g of Q were these two different sums of quotients. So we construct a grid. Okay, it's pairs of integers. The x-coordinate goes from 1 to phi of P over 2. The y-coordinate goes from 1 to phi of Q over 2. So here it is. The x's start at 1 and go up to phi of P over 2. The y-coordinate starts at 1 and goes up to phi of Q over 2. And I take all possible pairs. So from the smallest x-coordinate of 1 to the largest x-coordinate of phi of P over 2, the smallest y-coordinate of 1, the largest of phi of Q over 2, I take all possible points where both coordinates are integers. So there's a gap in here as we go from 1, 1, 1, 2, 1, 3, all the way up. But what we have is we have a piece of the integer grid. Okay, how many points are in it? Well, the x-coordinate has phi of P over 2 options, and the y-coordinate has phi of Q over 2 options. So the number of points in this grid is exactly phi of P over 2 times phi of Q over 2. So here is our grid of x and y coordinates. I claim if I pick a point AB in this grid, the y-coordinate over the x-coordinate is never equal to Q over P. If such a point existed, then B times P would equal Q times A. So P is definitely a factor of B times P. Since that's the same number as AQ, P would be a factor of A times Q. Now A was the x-coordinate of this point, which only is allowed to range from 1 to phi of P over 2. That's definitely smaller than P. So A is at least 1, but it can't be as large as P, so it's definitely relatively prime to P. Since P and Q are distinct primes, they're relatively prime to one another. Well, if P is relatively prime to A and also to Q, it's definitely relatively prime to AQ, so it can't be a factor of it. So P can't be a factor of AQ, so P can't be a factor of AQ. In other words, these ratios can't possibly be equal. So I'm going to draw a line of this slope, Q over P. The y-coordinate, B, can never equal that slope times the x-coordinate, A. Meaning, this line of this slope never intersects the grid that we drew. So if I draw the line of slope Q over P, it does not contain any points, A comma B, that satisfy this equation because B over A is never equal to Q over P. So I don't necessarily know exactly where this line goes, but it's definitely drawn to miss every point in the grid. So here is that grid. The x-coordinate goes from 1 to phi of p over 2. The y-coordinate goes from 1 to phi of q over 2. If we draw in the line y equals q over px, we know that this line misses all the points in the grid we drew. So since it misses every single point, there's a very clean way we can partition the grid into two sets. S1 and S2. S1 are points in the grid below the line, and S2 are the points in the grid above the line. Since the line doesn't ever hit the grid, there's no ambiguity here. So here's S1, points below, S2, points above. I'm going to color the points below the line red, so S1 are now red points. Simultaneously, we'll color the points above the line blue, so S2 are blue points. All right, here we have our grid. X goes from 1 to phi of p over 2. Y goes from 1 to phi of q over 2. The line y equals q over px misses all the points in the grid, so I partition it as S1 are the red points below the line, and S2 are the blue points above it. Notice, by the way, S1 is also to the right of the line, and S2 is to the left of it. Okay, so now let's look at S sub 1 in particular. Instead of just considering S1 as all the red points, I'm going to further partition it on a column by column basis. So for each possible x value going from 1 to phi of p over 2, notice that's the largest x value, phi of p over 2, and the smallest is 1. S sub 1 of I is going to be what are the points in S1 with that particular x-coordinate. Since the x-coordinate is fixed at I, this just means I'm looking at a column. So S sub 1 of 1 is just the red column where x equals 1. S sub 1 of 2 would be the points in the red set that are in this column. S sub 1 of 3 would be the red points in this column, and so forth, all the way until S sub 1 of phi of p over 2 would be all the red points in this column. Now I ask how many points are in one particular column. Pick a value of I. S1 of I is now all the red points in that column. How many points are there? So the x-coordinate is fixed, so I keep marching up until I would cross the line. The line is given by y is equal to q over px. So I keep counting up, I comma 1, I comma 2, and the last one I'll include is I comma k. In other words, that y value is less than the y value of the line, but the next y value would be above it. If I would exactly jump the line going from I comma k to I comma k plus 1, the y value on the line is q over px. So going from k to k plus 1 would jump the value q over p times I, because I have fixed my x-coordinate to be I. In other words, k is an integer less than q over pi, but k plus 1 is bigger. So q over p times I, rounded down, is exactly k. So how many points are there in S sub 1 of I? Exactly this quantity rounded down. Q over p times I rounded down. The total number of points in S1 can then be counted by adding up all of the columns. So how many points are there below the line? If I equals 1, this tells me how many points in the first column. If I equals 2, how many points in the second? And I count column by column from the first, second, third, all the way to the last one, which is phi of p over 2. So here, I'm counting up how many points in each column and adding it all up. On the one hand, that's how many points are in the red set. On the other hand, this is exactly g of q from Eisenstein's lemma. So the number of points below the line is exactly the g of q from Eisenstein's lemma. So the same picture we've had over and over. We've already determined that S1 has g of q different elements in it, and we did this by going column by column. Now we're going to look at S2 and view it as to the left of the line and go row by row. Define S2 of I to be all the points in S2 with a fixed y coordinate. Since the y coordinate is fixed, this does in fact split it up row by row. Similarly to before, we want to know how many points are in each row. Now in the column question, we said count the y-coordinates up until you cross the line. Here we would say count the x-coordinates up until you cross the line. And it's very similar to before, so I'm kind of going to gloss over it. But in the ith row, we're going to have exactly p over q times I different elements. So if I add up across all the rows, the number of points in S2 total will be the sum of all of the rows of how many points are in that row. But this sum is exactly f of p from Eisenstein's lemma. Now the line missed every point in the grid. So the number of points in the grid is exactly how many points are below the line plus how many points are to the left. There's no double counting here because I never actually hit a point. So therefore, the total number of points in the grid is how many are in S1 plus how many are in S2. Well, the number of points in S1 was g of q, and the number of points in S2 was f of p. Therefore, the number of points in the grid must be f of p plus g of q. But we already determined that the number of points in the grid is exactly phi of p over 2 times phi of q over 2. Because the x-coordinate goes from 1, 2, 3 up to phi of p over 2, the y-coordinate 1, 2, 3 up to phi of q over 2, so the total number of choices is just that product. So the number of points in the grid is either f of p plus g of q, or this product, phi of p over 2 times phi of q over 2. We already established through Eisenstein's lemma that the Legendre symbol p over q times the Legendre symbol q over p was -1 to this power. Therefore, the product is also -1 to this power, and that is exactly the law of quadratic reciprocity. So what have we done in total? We've established that if p and q are both odd, both prime, both different from each other, here's the law of quadratic reciprocity. But we already discussed that we can have the following form that we're actually going to lean on more frequently. P and Q, both odd, both prime, both different. Then the two Legendre symbols P over Q and Q over P are equal to each other if either of the primes is equivalent to 1 mod 4, but they are opposites of each other if both of them are equivalent to 3 modulo 4. And this is the version that we'll actually use in practical computation. And in the next video, we'll work through several examples to show why this result is actually quite amazing and vastly speeds up how to find Legendre symbols. You do need to be careful, however. P and Q have to be odd primes in order to apply this theorem. I can't tell you how many times I've seen students attempt to apply quadratic reciprocity when one of the numbers wasn't prime, or when one of the numbers wasn't odd. They both have to be odd primes in order to apply this result.